are going to talk about some linear programming, and this is really an application of all of the systems of linear inequalities that we've done. So I want to give you, first of all, some definitions of some things before we really talk about linear programming and all that it means. So basically, linear programming means a method of finding a maximum or minimum value of a linear function called the objective function that satisfies a given set of conditions called constraints. So we use this whenever we want to do to find a maximum number of things we want to sell or price or things like that, because there are certain conditions or constraints that determine how much products we have or how much money we have or how much time we have or whatever, and we want to use those resources in the best way to make the most profits. That's one example of linear programming. So a feasible region. So if I have a set of inequalities or system, so far we've only done systems with 2 inequalities, but we're going to be doing some with 3 and 4. And when you graph all of them, it'll make a shape like this. And this shape, inside of it, is called the feasible region. The feasible region is a set of points that satisfy the constraints in a linear programming problem. So basically, the same thing as what we did before, where we would find a solution to the system. This would be the solution to all of the equations or the systems. It just means that since there's more than 2, we're going to kind of have a boxed-in area. So if we had 3 lines, we might have a triangle or something like this, and the shape that it makes would be the feasible region. Okay, the constraints, one of the inequalities that define a feasible region in a linear programming problem. So the constraints are what we actually call the equations. These equations are called constraints. And the reason that you can think about it, to constrain something, you kind of like keep it in place. It's like the boundary lines. That's what constrains our, our feasible region. So a constraint is just the inequality equation. Then we also have what's called an objective function. So this is a separate inequality or equation that we use to determine what our maximum or minimum value is if we're trying to find that best value or something. So it's different than a constraint. The function to be maximized or minimized in a linear programming problem. The function may have a minimum, a maximum, neither or both, depending on the feasible region. So you can see down here, if it makes a shape like this, a closed shape, it's going to have both a minimum and a maximum value. You can have a feasible region that looks like this, that's not closed, it's not constrained or closed in. Then you're going to have either a maximum or a minimum, but not both. We're going to really be focusing on this kind of thing. So we will have a maximum and a minimum. So there are 5 steps to solving these problems, and these are really important. And they're written down here for you, but if you want to make notes to the side or put a big star next to something, this is really going to help you as we go through all these different problems. First step is to graph each inequality on a coordinate axis system. And it's really important that you are really precise about your graphings. If you don't shade on the right side of your line, it's going to mess up where your feasible region is, and then it's going to throw your whole problem off. Okay, so step 2 is find that feasible region by shading accordingly. So, when we did linear inequalities of systems of inequalities, we had 2 different color pencils. You might need more than that. It just kind of depends. Sometimes it kind of jumps right at you, and you can tell where the feasible region is. Third is to determine the vertices of the feasible region of the polygons that are formed. So vertices are those corner points. If you had a rectangle, these would be your vertices. But we might end up with some weird looking shapes, like this. But still, the corners are the vertices. So we're going to have to identify those as well as tell what the ordered pairs are that go with them. Then you're going to evaluate each coordinate in the objective quantity. That means we're going to take each of these points that we found from our feasible region and put it into that objective function. Remember, I said the objective function is not the same as a constraint because we don't graph it to determine what our shape is. We actually use it to determine what our max and minimum are. So then 5 is to determine the maximum, the highest value, or the minimum, the lowest value. by using substitution. Yeah, we're going to do that. By substitution. And that doesn't mean like substitution when we did systems. That's just, we're really just going to substitute in a point and solve the equation. So let's look at, first of all, here are three examples of, they already have the feasible region drawn. So we're going to kind of jump down towards the end. This is our objective function, and this is our feasible region here. So once we have a feasible region, then we're going to identify the vertices, and then we're going to find our points. So our points for this one are 0, 7, 1, 0, and 8, 0. And once we have that, so that means we're down here on number 3, because we did all the 1, 2, and 3. They did that for us. But we kind of want to look towards the end, and then we'll kind of build back up and go back to that. So just looking at this, our feasible region is done. We have an objective function, and we need to find what the maximum and minimum are. So by using substitution, that just means we're going to take our equation here, c equals x plus 2y. I'm going to start with, we'll call this green point here, 0, 7. So I'm going to put 0 in for x. I'm going to put 7 in for y. 0 plus 14, so c equals 14. Okay, that's the first point. Now I'm going to do the next point. The next point is 1, 0. So same equation. This time I'm going to put 1 in for x, and I'm going to put 0 in for y. That's just 0, so I end up with c equals 1. And the last point, 8, 0, same function. This time I'm going to put, 8 in for x, and 0 in for y again, and c equals 8. So my maximum is 14, and my minimum is 1. And that other one, 8, it doesn't mean anything. Okay, so we're going to have a maximum and a minimum, so one of them is not going to matter. All right, now this one has 4 points, so I'm going to have to do this 4 times. And again, I have to find the maximum and the minimum. We're going to do it the same way. You do have to do all 4 of them because you have to compare all 4 of them. So it's not like you can say, oh, I did the first 2 and I found it, because you have no idea if you found it without doing them all. So our equation is c equals 4x minus 2y. My pen just stopped working. There we go. Okay, so we're going to do, let's do -8 first. So I'm going to put -8 in for x, and -8 in for y. So 8 times 4, of course, is -32. And then 2 times 8 is going to give me a positive 16. And when I combine those, I'm going to get a negative 16. There's my red one. Okay, then let's do 2 negative 8. C equals 4x minus 2. X is 2. Oops, that's y is -8. We have 8 plus 16. C is 24. Okay. And we'll do 6 negative 2. Y is -2. 4 times 6 is 24. -2 times -2 is a positive 4. So C is 28. One left to do. -8 positive 4. -8, y is positive 4. 4 times -8 is -32. 2 times 4 is 8. And -32 and -8 is negative 40. So it looks like my minimum value is negative 40, and my maximum value is 28. Okay? All right, now the last one, if you want, you can pause the video and give that one a try. Now, the next one has 5 vertices, so I'm going to have to do this equation 5 times in order to find the maximum and the minimum. All right. So we'll start with this one, 80, 0. 3 times 80 plus 5 times 0. And this is 0, and 3 times 80 is 240. Equals 3x plus 5y. Let's do this one, 140. So 3 times 100 plus 5 times 40. 300 plus 200 is 300 plus 200. 100. 60 and 80. 180. 400. 580. 20 and 60. 20, 60, 60 plus 300. 3 is 360. And I got one more to do. C equals 3x plus 5y. X is 40. Y is 10. So 120 plus 50, 170. So it looks like my maximum value is going to be 580, and my minimum value is 170. Okay, so that's how we find our maximum and our minimum values. Now, we're going to back up and we're going to graph ourselves this time. So I'm going to start by graphing my constraints. Now this one up at the top is the objective function. Usually it has 3 variables in it. I couldn't graph that anyway because I don't have anything for here. So C might mean cost, or it might mean P, which is profit, or something like that. So these 3 here are my actual constraints. So X is greater than 0. I'm going to have a line right here, and I'm going to graph X greater than that, which means I'm going to go up. I'm not going to get too crazy with the shading right now. Then I have, oh, wait a minute, that's Y is equal to 0, or greater than 0, sorry. That's this one. Then we're going to go up here and do X is greater than 0, which is this direction. So we know everything is going to be in the positive quadrant, right? And then the last one then is this one. I do my zeros. I put 0 in for X, Y is 5, 0 in for Y, and X is 5. So here and here. And if I draw my line. Now I do need to decide though if this is, which direction I'm going to shade. Now, I'm guessing it's going to be in here, but I'm going to test just to make sure. So I'm going to put 0 in here. 0, 0. 0 is less than 5. That's true. So here is my feasible region. And these are my points. 0, 5, 5, 0, and 0, 0. So in order to find my maximum and minimum, I have to use those 3 points. In my function here. So C equals 3 times 0 plus 4 times 0. So C is equal to 0. That's the first one. C is equal to 3 times 5 plus 4 times 0. So C is equal to 15. And the last one, 0 and 4 times 5. So C is equal to 20. So my minimum is 0 and my maximum is 1. Okay. X is less than 5. Here is X equal to 5, and if I want X less than that, I'm going to be looking at this side here. Y is greater than 3. So then Y is 3, and Y is greater than is up here. And then my last one, oops. So if I put 0 in, I end up with 30 divided by 5, which of course is 6. And then if I go back and do the other one, 0 in here, it's 10. So 0, 6, and 10, 0. Okay. I'm going to put in 0, 0 for my test point. I think that whole thing over there, 0. So 0 is less than 30 is true, so I want to shape this direction. And it looks like this is my feasible region. Now, be careful because that is not a triangle. Because it doesn't come all the way to here. This red mark makes it stop, so I actually have 4 vertices here. Okay? So this one is 0, 6. This one is 0, 3. And this one is 5, 3. And this one is 5. That looks like a fraction. I've got so much drawing on here, I can't tell. I wonder if I had drawn my line nice and straight, if that would have happened. Let me see. I want to make sure, because especially since I'm dealing with a point there, 5y negative 3x plus 30. I'm going to find my slope. Count some points this way and see if I can make sure I get exactly the right number. So, down 3, 1, 2, 3 over 1, 2, 3, 4, 5. Oh yeah, see, it was right on the line and I didn't draw it straight. Okay, that's good, because that makes it a triangle instead. So that means we have the point 5, 3. Okay, so a triangle, good. Make sure you use your ruler. You want this to be perfect. If you don't have that line drawn straight, you're just going to cause a mess. So, all right. So now we have our 3 points. We can plug them into our constraints and see what our max and min is. So 2 times 0 plus 5 times 6. So C is 30. one is 2 times 0 plus 5 times 3, so C is 15. And then the last one is 2 times 5 plus 5 times 3, 10 plus 15, which is 25. So our maximum is 30 and our minimum is 15. All right.